Hello. Yes, we welcome you back to PSSB, Physical Sciences Silver Bullet, and it's me, Richard, here. Yes, tonight we are looking at this question. It says, state work energy theorem. How does it state? It states that the net work done on an object is equal to object's change in kinetic energy. Yeah, so comes this question. It says that a car of mass 1,200 kilograms is moving up the inclined plane at constant velocity of 5 meters per second. The work done on the car by friction force is given, and the work done by an engine is also given. The car covers a displacement of 10 meters, and here we have the sketch. So the question says, draw free body diagram showing all forces which are acting on the car. Okay, how do you go about this? Okay, we have the incline, and it's a free body diagram, so we have that body as a dot, and we say that the car is moving with constant velocity. Now I want you to know that there is no under any circumstance a car can move up the incline with constant velocity without applied force. So applied force is a must. So which other forces are acting on this car? Okay, we saw work done by friction force, implying that there is friction force. Okay, what else do we know? We know that there's that component of gravitational force always acting downwards. Okay, so if this is our horizontal, we have our angle of inclination. What other force do we know? The car is sitting on the ground, so there is normal force. And we have our FG perpendicular, or the perpendicular component of gravitational force. So these are the forces which are acting on the car. Yeah, so comes this question. It says, calculate the net work done on the car. How do you go about that? Okay, to approach this question, we'll read the free body diagram. Okay, let's trace it again. We said we have our applied force, and we said we have our friction force, and we have also our parallel component of gravitational force. If that's the case, then what do? We recall from work energy theorem that net work done on an object is equal to net force delta x, but we have also to recall or to remember that F net, if you look at our free body diagram, is going to be equal to the FA minus FG parallel minus FK. Yeah, we are using the concept that net force is equal to sum of forces where the body is going minus sum of the forces where the body is coming from. So when you substitute F net here, what are we going to get? We are going to get net work done as FA minus FG parallel minus FK into delta X. When you expand this one, what are we going to get? You get network done equaling to FA delta X minus FG parallel delta X minus FK delta X. So here we are. But I want us to recall that every time you have a force multiplied by displacement, what you get is work. And if you have force multiplied by displacement here, it's going to be work done by friction force. And this one is going to be work done by gravitational force. Now, I want us to recall that we are given this and we are given this. We know their values. What we don't know is that one. So from this equation, we know work done by applied force. We know work done by friction force. We can also calculate work done by gravitational force. Let's try it here. If you have Fg parallel delta X, if you expand it, you are going to get mg sine alpha delta X. Do we know m? Yes. I think we know the mass of the car, which is 1,200. And we know g, which is 9.8. The angle is sine 25 degrees. And times displacement, which is 10. What you get here is going to be work done by gravitational force. Yeah, so we know work done by gravitational force. So we can now go ahead and substitute in each of these. Okay, let's start and we see. If this is our network done, then what is work done by applied force? It is 2 times 10 power 5 minus, okay, what is work done by gravitational force? It is 49699.91 minus, what is work done by friction force? It is 2 times 10 power 4. Yes. What we get out of that is going to be our work done by net force. Yeah, there we are. That is it. Our net work done on the car is this: 130,300.09 joules. Yeah, so comes this question. It says that the initial velocity of the car at the bottom of incline is 22 meters per second. Calculate the final velocity of the car at the top of the incline. Okay. How do we go about that? Okay, here we apply work energy theorem, which is this. Okay, What does this mean? It means that network done on the car is equal to a half mvf squared minus a half mvi squared. Okay, so from there you need to know that we know network done. Yeah, which is this. What else do we know? We know VI, which is 22 meters per second. So when we substitute for those, what do we get? We are going to substitute for this, and we have it as that. Okay. Then we have a half. The mass of the car is known. It is 1,200. And we know the final velocity. No, we don't know it, but we are looking for it. But we know the initial, which comes with this. Yes, there we are. Yeah, so from here, what do? We collect like terms, and we have our network here, plus this, which will give you this. So that is what we get. Then from here, let us squeeze something here. We can say that 701.17 is equal to VF squared. So our VF is going to be equal to 26.48 meters per second. And that is the velocity of the car at the top of the hill or at the top of the incline. Yeah, with that, would like to thank you for your time. The channel is PSSB, Physical Sciences, Silver Bullet. Yeah, see you next time. Don't forget to subscribe, to like, to comment, to share. Yes, we are simply the best. See you next time. Bye bye.